video is going to talk a little bit about the resultant forces and how we can use vectors to model real-world situations. So you'll notice we're just going to go through a couple examples today using or taking advantage of the trig form of a vector. So again, if you're not familiar with the trig form of a vector, it's basically the magnitude of a vector. So let's say we were working with a vector v, its magnitude multiplied by the vector cosine of the angle direction, or the direction of that vector, comma, the sine, right, of that angle. And again, that just comes from the sort of a unit circle idea, right? Cosine and sine being the horizontal and vertical components of any angle in the unit circle. And then if we multiply by the magnitude, right, that stretches our vector to be the length that we need, right? Again, if you need to know about trig form and you're not familiar with that, feel free. There's another video. It talks all about trig form. So make sure you rewatch that sometime before maybe watching this video. But otherwise, the idea here is the outcome of two forces acting in unison, sort of acting upon each other, is simply given by the sum, right, of two force vectors. So what we can do is sort of draw this out. And notice in this example, we've got two men pulling on ropes. The ropes are going to be at a 35-degree angle to each other. And one man's pulling with a 40-degree force, the other's pulling with a 40-pound force, and a 50-pound force on the other rope. We want to know the magnitude of the resulting force, right? If they were both pulling in unison or sort of on the same rope, we'd obviously have a 90-pound force. But because one's going to pull sort of one direction, right, and then another is going to pull at that 35-degree angle, right, but in the other direction. So this one's the 40-pound force and this one's the 50-pound force, right? Since they're not pulling directly with one another, remember that when we do that sort of tip-to-tail drawing, that tip-to-tail method, right, they're both pulling. Our resultant is going to sort of split the difference here. It's going to pull sort of through the middle. But now it's not going to be perfectly in half because, again, one's pulling harder than the other one, right? So our angle is going to be sort of off just a little bit there. So let's take a look and see how we can take advantage of that trig form idea to help us out. Since they didn't give us any actual direction angles, I'm going to make this first vector, so sort of this bottom one, right, that 40-pound vector, I'm going to go ahead and put that at 0 degrees because I can kind of decide to put it wherever I want to put it. So again, that basically tells us we're going to do 40 times the cosine of 0 degrees, sine of 0 degrees. And again, the reason I'm going to do that is the cosine at 0, remember, is equal to 1, and the sine of 0 degrees is equal to 0. So if I actually shorten that a little bit, well, 40 times cosine 0 is really just 40, and 40 times the sine of 0 is 40 times 0, well, that's really just 0. And it kind of makes sense. Our blue vector traveled directly to the right. It's horizontally 40. Vertically, we didn't go up and down at all, right? So again, it makes sense that we'd have a vector of 40, 0. Then let's add on, right? We're going to pull with both ropes. So we're going to add on that 50-pound vector, only this time it needs to be at a 35-degree angle. So we're going to be cosine of 35, comma, sine of 35, right? Make sure we use those vector symbols there, right? Those vector brackets. Well, if we add those two things together, basically we're saying 40 for the horizontal plus 50 cosine 35, right, for the horizontal of the other vector, comma, 0 plus 50 sine of a 35-degree angle, right? We're going to add the horizontals to the horizontals and the verticals to the verticals. And now we can go find that magnitude, right? If this is going to be my resultant vector, right, we can find the magnitude of that vector, and let's use all the right symbols here, by saying square root of, and all we have to do is type those numbers in. Now, we could go find those ahead of time, which isn't a bad idea. So if we hop on our calculator here, we can say, again, 40 plus 50, the cosine of, again, 35 degrees. And we'll find out that we were 80.9576. So this one was really 80.9576, which down here is going to be the same thing, 80.9576, right, squared plus, and again we could just go back to our calculator, 50 sine 35, which is 28.679. 28.679, which really looking at, right? Looking at our picture, that makes sense. We traveled far to the right, right? Looking at that orange line, but we only traveled a little bit up, wouldn't be even 50 up, right? 28 upwards for that orange line there. So the vertical is not too tall. Now, when I go to type these back into the calculator, I want to be careful that I don't use these rounded numbers to try to find my magnitude. So one way that I can do that is if I just use my copy paste on my calculator here. I'm going to say second square root. I'm going to throw a parenthesis on there, and then I'm going to go back up. I'm not going to grab the rounded number. I'm actually going to grab the original statement. I'm going to grab 40 plus 50 cosine 35, but at least that saves me from having to retype it. And then I'll put another parenthesis squared. Plus, and notice I'm still underneath my square root, I'm going to say parentheses. Let's go get that 50 sine 35. Close that one off, square that one, and we should have a magnitude of 85.887. So again, we're going to be about 85.887. And notice that our magnitudes up top are measured in pounds, so let's call that pounds. Okay. So we've got that handled there. Let's go try another example and kind of see where this really comes into play. One really good example is with airplanes. All right, one really good example is with airplanes. An airplane's traveling at a speed of 520 miles per hour, but again, the wind is going to blow us off course. So we're supposed to be traveling at 330 degrees. Now remember, if they don't give us north, south, east, or west, that means in a clockwise, right, from north direction. So 330 degrees is essentially going to be way up here, right, doing this thing clockwise around there. Or notice they even said north 30 degrees to the west. So from north here, right, we would go 30 degrees directly to the west. So we kind of know what our angles are looking like on that. But again, that's at 520 miles per hour, and 520 is going to be our magnitude then, right? Well, the wind, on the other hand, is blowing from the west. So from the west, going this direction, right, straight from the west, essentially blowing due east, but it's blowing at 15 miles per hour. So it's a much shorter, right, line there. And if we do our tip to tail, right, the plane would be flying on the blue line, but again, the wind is blowing to the right, at 15 miles an hour. Should be a lot shorter than the 520. So I'm thinking we'll still end up here in quadrant 2. But our resultant then is that our plane got blown off course. Instead of flying at 330, we're flying inside of that just a little ways, right? We're going to be flying just a little to the right of that. And probably a little slower, right? That looks like that red line. It's a little bit of a headwind, right? Just a little bit, slowing the plane down a little bit. So I would fully expect, notice they're going to ask us to find the speed and the direction of the plane. Speed being magnitude, and again, the direction being that bearing idea. So let's go ahead. Let's start by writing out our vectors. So we've got 520 times the cosine. Now I got to be a little bit careful here. Notice that again, our 30 degrees over into quadrant 2, but when we measure angles, we go from the positive x-axis, right? So what would this angle have ended up being? Well, I'm thinking that if that's 30 degrees over there, that's 120 degrees from the positive x-axis. Remember, we always want to measure our angles so that both vectors are sort of being measured from the same place, right, from that positive x-axis. Plus, we got to write a vector for the wind. Now notice that one's at 0 degrees, so much like our last example, that red line's directly to the right. It's probably a little easier if I just say, well, hey, that's just the vector 15, 0. We went right, but we didn't go up. Now we can add them together and get our resultant, right? So we're going to essentially be 520, the cosine of 120 degrees, plus 15, comma, 520, the sine of 120 degrees, but again, plus 0, right? So we don't really need to go find that one. Again, that's our resultant R, right? Now we could find those numbers, which would be a good idea. So let's hop on the calculator and get that done. So again, we're going to be 520 cosine 120, make sure you close that cosine, plus 15, so negative 245. Oop, got a little problem there. Negative 245, right? Oops, not an angle there. And then we'll type in, again, 520, the sine of, oops, 520 here, the sine of 120. And again, that'll be 450.333. So 450.333 there. We want to go back and get our magnitude, so feel free to pause the video and get ahead of me on that one. But essentially, again, we're just going to take our negative 245, right, square it, plus our 450.333 squared. And again, we can toss that straight into the calculator. Again, I'm going to use that shortcut idea. So I'm going to say parentheses and squared plus, again, we'll go get that sine. And now notice I forgot to close that one. So now I close that and square it. And we should be about 512. Remember we said we were going a little slower. So 512.665. And again, we're still in miles per hour, but a little bit slower, right? The wind slowed the plane down. And then we need to go get our angle. Now remember, the tangent equals B over A. Tangent equals vertical over horizontal. So the inverse tangent, right, of the vertical divided by the horizontal. So theta should end up being equal to, right? That'll end up being theta. Theta should end up being equal to, well, let's take advantage again of those pre-typed numbers. All I have to do is go grab the sine here and divide that, right? Divide that, so I better, yeah, I think I should be okay. It's just multiplied, so divided by, make sure you throw a parenthesis here though, because the next statement's got some addition in it. Got to make sure it adds before we end up doing our division. And we should end up with negative 61.452. Now I have a problem with that. Oops, 452 there. Number one, I have a problem with that because I wrote it wrong. But 0.452. 61 degrees would be down in quadrant 4 though, right? We'd be down this way. Notice we want to be up in quadrant 2, so we need to be up that way. Well, remember, your reference angles are equal. So what I want to do is just go ahead and add 180, right, to that angle. So back on the calculator here, let's add 180. And I would much prefer 118.548. 118.548 degrees. So that would be a good direction angle, right, for theta. And if you wanted to write that as a bearing, well, remember, since the original bearing was written from north, all we would have to do is work our way around this way, right? Measure our bearing all the way around. So what I would want to do is figure out this angle in between. Well, if I take off the 90-degree angle over here, so that'd be about 28, right? 0.4548 degrees, okay? So that we could say north, right, to the west of that. Or I can take 360 minus that, right? So I'll hop on the calculator real quick again. We'll subtract our 90, looks good, and take 360 minus that answer. And we get 331.452. And again, that would be a much better bearing. Again, I hope that helps you with bearings and directions. If you have any questions about vectors, make sure you talk to your teacher. Otherwise, have a great day.